Let's solve the equation AX is equal to B. A is a 3 by 3, B is a 3 by 2, so X is also a 3 by 2. We can partition B and partition X into two columns, and I can think of those columns as being X0 and X1. So if I notice, though, B actually has some special properties in that if I look at the columns and I think of them as being B0, B1, B1 is actually negative B0, which means if I'm trying to solve or find the X that solves this system, there's a relationship also between X1 and X0. In fact, X1 has to be equal to negative X0. So it actually can save me quite a bit of work by noticing this. If I want to solve this system, I like to use appended matrices in order to do it. And actually, all I need to do is solve the system 1, 0, negative 1, 3, negative 1, 0, 0, negative 1, 1 times X sub 0 is equal to negative 2, negative 1, 3. Use that result to find the matrix X. So let's do it. Let's use Gauss Transforms in order to do this. In other words, I'm going to put this system, find an equivalent system that is an upper triangular system, and then use backward substitution. So the first thing I notice is what I want to do is zero out the first column here, and in order to do that I need to zero out this 3, which means the Gauss transform to do this will have a first row 1, 0, 0, leaving the first row here the same, but the second row I'm going to have to multiply the first row by negative 3 and add it to the second row in order to zero out that entry. And then the last row has a 0 already in that entry, so I can leave it as is. And so my Gauss transform will look like this. And when I do this, the first row stays the same. The second row, I multiply the first row by negative 3 and add. I end up with 0, negative 1. Then negative 3 times negative 1 is positive 3. Adding it to 0, I end up with a 3 in this entry. Then negative 3 times negative 2 is positive 6. Minus 1 is positive 5. And the last row stays the same. Next stage, I need to zero out the second entry in the last row. And to do this, first row is going to stay the same, second row is going to stay the same, but the last row is going to be updated by, we need to multiply the second row by negative 1 and add to the third row. So the Gauss transform will have entries in the last row of 0, negative 1, 1. The result will be 1, 0, negative 1, negative 2 in the first row as before, a 0, negative 1, 3, 5. Same as before in the second row, but now the last row becomes 0, 0, and then negative 1 times 3 is negative 3, plus 1 is negative 2, and negative 1 times 5 is negative 5, plus 3 is negative 2. So now I have my upper triangular system, and I need to use backward substitution, which means that if x sub 0 is made up of the components chi0, chi1, chi2, we know that negative 2 times chi2 is equal to negative 2, which means that chi2 must be equal to 1. We also know that negative 1 times chi1 plus 3 times chi2 must be equal to 5, which means that negative 1 chi1 must be equal to 2, so chi1 must be negative 2. And then also we know that 1 times chi0 plus 0 times chi1 minus 1 times chi2 must be equal to negative 2, which means that chi0 minus 1 is negative 2, which means chi0 must be equal to negative 1. Then we have x0, which means x must be the matrix with columns negative 1, negative 2, 1, and 1, 2, negative 1. Again, by the argument I made before I started. Okay, was there another way that we could have solved this? Sure. We could have found A inverse, and then x would have been A inverse times B. Is there another way? Sure. What we could have done is we could have found the LU factorization for A, then used backward substitution and forward substitution to find x. So there are actually several different ways that we could have used in order to solve this system. I just like to use appended matrices, so that's my favorite. That's why I did it in this fashion.